All right. Okay, so this is the second section of Chapter 1, Lesson 2, and what we're going to do is look at the symmetry of graphs. And so we're going to look at the symmetry of graphs, and we're going to look at if graphs are odd and even. Please, no matter what on this section, remember it, because when we get the trigonometry, this becomes a very big deal. All right, so there's 3 types of symmetry with graphs. Now, are all graphs symmetric? Absolutely not. But there is some cases they are. So here are the 3 cases. Number 1, if it is symmetric to the x-axis. Basically what that means, if I took the x-axis, I fold the graph on half, and it will land perfectly on each other. So if I folded this, it would be on it. What it is then, the x values are the same, and the y values are opposite. And to prove it algebraically, you would put in the opposite y value to figure out if the rest of the equation would be the same. Okay, the next one is if it's symmetric to the y-axis. So if I folded it on the y-axis, it would fold perfectly on each other. The y values are the same, but the x values are opposite. If you forgot opposite, one's positive, one's negative. And you would do this to make sure the equation is equivalent by replacing the x with a negative x. And then the third thing is if it's symmetric to the origin. So if I was to, you have to do like a certain kind of fold. But if I was to fold it, it would land directly on each other. But both x's are opposite, and both x and y is opposite. So here's like positives and here's negative. If they were in these 2 quadrants, then one would be negative, one would be positive, and then the other would be opposite. You would figure out the equivalent equation by plugging in a negative x for x and a negative y for y. So let's look at 2 graphs. We have this graph and we have this graph. So we're going to look at this one first. By just looking at it, we can say it's symmetric to the y-axis. It's pretty simple there. You can look at the points that prove it numerically. This is a good point. We're going to do this point and this point. This point goes by 2's again, 2 and 2. This point is 2 and negative 2. The x's are the same. Good lord. The y's are the same, but the x's are opposite. Or the y's are the same and the x's are opposite. That's proving it numerically. To prove it algebraically, here's the original equation. I'm going to plug in a negative x for x, and I'm going to simplify it. Now, a lot of people just try to make that positive right away, but please, parentheses first and exponents. So here's a negative. Negative x squared squared is just x squared. The 2 equations are equivalent, so we just proved that it is symmetric to the y-axis. So this one's symmetric to the y-axis. So let's look at this one. This circle, it's symmetric to the y-axis, the x-axis, and the origin. If I fold it on the y, it's perfect. If I fold it on the x, it's perfect. If I fold it at the origin, it's perfect. But look at it. Let's prove it numerically. I'm going to say about 4. So this is about 4 point something. We'll say 4.2 and 0. This is about negative 4.2 and 0. So we just proved that, or numerically we just saw that it is symmetric to the y-axis. We can do the same with the x and be about the same numbers. Let's prove some of it algebraically. Okay, well, this is for the x. So if I was to prove it for the x, I need to plug in, here's the original equation, go plug in a negative y. Negative y squared. So this becomes x squared plus y squared equals 25. The equations are equivalent, hence it is symmetric to the x-axis. If I did the y, I got, I'm going to plug it in for the x. So here's the original. X squared plus y squared equals 25. I'm plugging in a negative x for x squared. And that just becomes x squared. So it is also equivalent to the y-axis. Because the x and because the y worked, we can say it's also equivalent to the origin. But that's all you're doing to prove it is. You're just proving in the opposite of the other variable. X-axis, you plug in negative y. Y-axis, you plug in negative x. Origin, you plug in both. But that's how you figure out symmetry. All right, odd and even functions. This is the big one. An odd function is symmetric to the origin. An even function is symmetric to the y-axis. So we're going to do this one first. If I plug in f of x, the original equation is f of x, and we're going to plug in negative x, 2 over negative x squared. So f of negative x equals 2 over x squared. They're equivalent. So hence, this is an even function. So it's the same as proving the symmetry to the y-axis. Now, to prove it's an odd function, it's a little bit different because we're not using x and y, we're using f of x. So you do the same thing, you're going to plug in negative x. So I get negative x to the third minus 2 times negative x. Negative x to the third is negative x to the third. Negative 2 and negative x is plus 2x. So what happened is, it's opposites, which is what the odd, or what a symmetric to the origin was. So because it is opposites, positive, negative, negative, positive, it is symmetric to the origin. And so therefore, it is an odd function. And that's an easy way to remember it. Origin starts with O, odd starts with O. So just a lot of algebra, you're going to have to be good at it. But your homework for the last homework for chapter 1, lesson 2 is page 19, 24 through 41. All good luck.